What is a hash map? Before we learn what is a hash map, or a hash set, we should know the building blocks of data structures. The fundamental deciding factor of which data structure you want to use mostly narrows down to how you want to store the elements and how you want to access them. There are many data structures we know of like array lists, stacks, queues, binary trees, and graphs. Those are mainly derived from either an array or a linked list. So we should first clear our understanding of both an array and a linked list. Starting with, what is an array? Imagine this as your memory, and each block or square in this represents memory locations of 4 bytes each. In most modern programming languages, an integer occupies 4 bytes. An array stores the elements in contiguous memory locations. The arrays marked by indices starting with 0 are stored in contiguous bytes in memory, 1 byte after another. Arrays also have a finite size, meaning they are bounded. This is not a feature, but a limitation. But why is it a limitation? It is clearly evident from the nature of how an array is stored that you need the memory allocation to stop at a certain point, because it needs contiguous blocks of memory, and the memory is finite, and in this very memory other programs also live that are running on your computer, and each program needs memory to run. Hence, whenever you declare an array, you must define the size. Now for the best part of arrays. You can access an index directly, meaning you can reach an element via its index in order of one-time complexity. We will see this with an example soon. As there are good parts, there are bad parts as well, which is wastage of unused space in an array. The reason for that is since you need to define the size of an array up front, there is a chance that you don't have all the elements to store in the array. In an array of size 10, you may only ever need to store 6 elements in it, which is a 40% waste of memory. This fact is mostly ignored in production applications or most modern programming languages. A classic example of that is an array list. As a quick example, when an element is added to an array list and there isn't enough space in the underlying array to accommodate it, the array list automatically increases its size to nearly 50% more. So an initial array list of size 6 may increase to size 9 after it fills up, but you may never store more elements in it, which results in unused occupied memory. The mechanism for this resizing involves creating a new array with a larger capacity and copying the elements from the old array to the new one. This larger capacity is usually 50% more of the initial capacity, and resizing happens when the original array has reached a certain threshold like 80% of its size. But it can vary based on the language runtime, and once the copying is done, the original array's memory is freed to be used by other programs. So now you know an array list is backed by an underlying array data structure. It's important to know how they fundamentally work. Now, let's go back to arrays and take a look at an example. You declare an integer array of numbers with size 9, which is mandatory, or you can also pre-initialize the array at the time of declaration. Size is fixed here as well by the number of elements you declare. Now, you can retrieve an element at index 7 in constant order of one time using a simple calculation. You already have numbers variable that points to the memory of start of the array, call it M. Then you can reach 7th index jumping the 7 blocks of memory from the start location. Each block of memory is the byte size, which is 4 in case of integers. You can also change the value at an index by simply going to the memory location via the index and updating the new value. It is the same constant time. This is what we had to know about arrays. Now, let us look at what is a linked list. Again, imagine this as your memory. As opposed to arrays, linked lists are not contiguously stored in the memory. In the two examples, the memory blocks that are used by the linked list are not contiguous. They also do not have to be adjacent to each other. A linked list is also unbounded and can grow to any length without having to copy to a new location. Let us understand this behavior. Imagine that the grayed-out blocks of memory are occupied by other programs running in your computer. So, when you want to create a linked list, the system finds a free block of memory and then another free block linked to the previous one, and then another, and another. For this very fact, a linked list can keep growing by finding free blocks of memory, and you can keep on adding the elements. It is only limited by the size of overall memory itself. As opposed to arrays, a linked list does not have index-based access, and you can only access elements via a next pointer. We will see an example soon. Also, as we saw earlier, that ArrayList could have unused memory, but in case of LinkedList, there is no unused memory. Now imagine that you want to store these 5 integers, 15, 6, 7, 9, and 10, in the linked list. You start with creating a node that stores the number 15. And in order to reach number 6, you have to have a next pointer in node 15, pointing to the node 6. Similarly, from node 6, you can reach the next node 7. And so on. You cannot jump to elements in a linked list, because remember, there is no index-based access, and you can only go to the next item sequentially. There are 2 special nodes in a linked list. The first one is head node, which is the very first node you create when you declare a linked list. The head node's next pointer will point to the first integer in our list. Alternatively, you can also make the first integer itself as the head node, but for a clear design, we usually create a separate head node. The second special node is the tail node, which will always be the last node in the linked list. And since it's the last node, the next pointer of tail node points to null, and the last integer in our list will point to tail node. A simple declaration of a node class is like this in pseudocode, which contains the integer number and a next pointer reference of type node itself. Now, when you want to access an element in a list, let's say you want to access integer 7, then you start with head node and call next to reach node 15, and again call next to reach node 6, and again next to reach your destination node 7. This results in order of n-time complexity to access an element. Similarly, if you have to change the value of a node, you will have to traverse from head node to access it, and then change its value, which is also order of n-time. At this point, we are clear of our fundamental understanding of array and linked list, so let us now have a look at how the HashMap works. A HashMap is a pair of key and value, where all the lookups happen on the key, and the way we store entries of these key-value pairs also happen on the value of key. A key could be any data type, but for our example, we would assume both the key and value to be of type string. A HashMap derives its name from the use of a hash function, so we should first understand what a hash function does. A hash function takes an input and produces an integer output with 2 fundamental characteristics. Let's see them one by one. First, the hash of same input will always produce same value. That is, if you compute hash of a key multiple times, it is guaranteed to produce same output every time. The hash of keys 1, 2, and 3 are different, and if you compute the hash of key 1 again at a later point in time, it will produce same output. Second, 2 different inputs can end up having the same hash value as well. So hash of key 5 can produce the same output as hash of key 2. This is called a hash collision, and we will see what happens during a hash collision in the HashMap. Now let us look at how a HashMap is stored in memory using a combination of both an array and a linked list. In HashMap, the operation to add a key value entry is called a put, and the operation to retrieve value for a key is called a get. During the put operation, we first decide which bucket the key should go to. These buckets are nothing but indices of an array. Let us keep the size of array as 16 to start with. As the next step, we first calculate the hash of the key. Hash of string key 1 will give you an integer value, which is quite a big number. To fit this into an array of fixed size, we run this number through a modulo function where the result will always give us a value between 0 and size of the array minus 1. So this number modulo 16 will give us 1. So this key will go to index 1 or bucket 1, 1 of the array. Similarly, key 2 hashes to index 2 and key 12 hashes to index 15. Now let's take a look at what happens during a hash collision. Let's try and add key 26. This hashes to index 2, and there's already a key at this index, which means there's a collision. This isn't exactly a hash collision, but a collision in our array due to the modulo function. But in case of exact hash collision as well, the behavior is the same. This is where linked list comes into the picture. So in this scenario, we will use a linked list at that particular bucket to connect the keys which hash to the same bucket. Here first, all the keys at that bucket will be traversed and compared to the key you want to put, and if the key is found, the value is updated at that node, and if the key is not found, then it is inserted at the end of the linked list. So key 2 will have a next pointer pointing to key 26. Similarly, if we want to add key 37, it also hashes to index 2 or bucket 2, so there will be a pointer from key 26 to key 37. If there is nothing after key 37, it points to null. Key 45 also gives a collision by hashing to bucket 15, so it also becomes a linked list, and previous key 12's next pointer points to key 45. An important point to note that in case of some programming languages like latest versions of Java, the linked list is converted to a red-black tree in case of high number of collisions in a particular bucket. This is due to the fact that insert operations for a very large linked list will be order of k, where k is the size of the list, which is inefficient. Comparing that to a red-black tree, the insert operation will be order of log k, which is an improvement in performance. Now let us look at the time complexity of adding a key to a hash map. The time complexity for a get operation is similar to put. The steps involved are: calculate the hash of key, which is constant time. Then identify the bucket using the modulo operation, which is also constant time. Then find out whether there is collision in that bucket or not. In case of no collision, the key is inserted straight away in constant time. In case of less collision, the key is compared with every key on the linked list using equals function, and it is either updated where found or inserted at the end. This complexity is order of k, where k is the size of the linked list. The third case is when you have very high collisions, in which case the linked list is converted to a red-black tree for better write performance, and adding a key in this red-black tree gives us more efficient time complexity of order of log k. Now, since we had discussed earlier that an array list grows its size automatically based upon the load factor, the same case applies for the array that a hash map uses to store buckets. This array increases its size automatically by copying to a new memory location, and here it also needs to do rehashing, since it needs to calculate the hash of each and every key already present in the hash map. This is all hidden from the end user, since it is internal structure of how an array resizes and rehashes. But all we need to worry about is that the hash function itself does not change, and it will still produce the same hash of each key. But when you do modulo operation, the bucket of keys could change, resulting in new bucket assignments, and here number of collisions could reduce, since number of buckets are greater than before. Given this fact, on an average case, a hash map tries to keep as low collisions as possible, and if needed, it resizes. In such a case of no collisions, the bucket will only contain one key, which gives us constant time complexity of O1, order of 1 for lookup. But in some real-life production scenarios, collisions will be there since they cannot be avoided when the hash map contains large amount of keys. This is all about the hash map. In case you liked, do subscribe for more upcoming videos on data structures and algorithms. Until next time, goodbye.